bottle chamber is a particle detector which makes use of electric and magnetic fields. Explain the roles of electric and magnetic fields in a particle detector. Should be a nice little bit of revision for us. Thinking about what we've done, the first thing we should be thinking about is the fact that it wants electric and magnetic field. Yes. So let's just think about like sketching it out. What are going to be our main points to be considering here? For electric fields, what are they? What are we doing with electric fields? They accelerate. So the electric field's there to accelerate. What about the magnetic field? What's that there for? To deflect. Okay, so thinking about the electric field, what can it accelerate? What can it do? What kind of things might we want to throw into our answer here? Yeah, definitely. We're probably definitely going to want to say accelerate charged particles. Is there any maths or formulas we can throw in here?
It's kq1.
No, F is not kq1 q2 over r squared. F is only kq1 q2 eq. F is eq. Thank you very much. It's only that formula for single point charges. These don't apply to particle accelerators. Okay? What about magnetic fields? What do they do? Okay, so they cause a force perpendicular to velocity. You might want to mention Fleming's left-hand rule. What else? What's going to be a useful thing to say as well? Thinking about what we've done here. What's the equation going to be? What's the analogous equation for magnetic fields? Not Bev. We don't say Bev, we say BQV. Really, really important to remember that it is BQV, not BEV, because Q is for any charge. Right? Not just in electrons anymore. Okay. Is that it? Is there anything else we can say? Well, let's think about an ordinary particle accelerator. Thinking about magnetic fields. If I wrote R equals, what do we get there? P over VQ, where P is mv, yeah, very good. Bar, because it's accelerating, could I rewrite this force equation in terms of an acceleration? F is EQ over F. F is EQ over F. Yep. That's good. That's actually not to gain any more. And the one thing that we might want to say is that it causes it to deflect, and what I'd like you just to add is it deflects with circular motion. Okay? And that's all you need for that one. So we've got the positively charged particles in the solar wind are accelerating away from the sun. Some scientists have therefore concluded that the sun is positively charged. Explain this conclusion. What's going on in this question? Why is this happening? Yeah. So we've got a positive sun. Yellow sun.
Sun.
Yeah, so there's the sun, and we're going to call that positively charged. If I have a positive charge here, what's that going to do? What's that theory saying? Yeah. So there's going to be a force on the particle, force on the sun. The two are going to mutually repel. Yeah. So why is that going to cause an acceleration?
Because that is FA.
Okay. Have we explained why it's accelerating the react? What does that force do to cause an acceleration? Seriously? F is an Yeah! Easy. You can say because F is equal to ma, so therefore a force from repulsion causes acceleration. Does that seem reasonable? Okay, let's just check the old mark scheme. And what they were after was... Okay, got light charges repelled, that should be fine. What's the next bit?
Explicit statement relating force repulsion to acceleration.
And we've said that force is equal to acceleration, so we've picked up all the marks. Easy, right? Okay, so we've got complete circles into sun, complete the diagram to electric field. What are you going to do?
Although there's not a straight line.
Oh no, not straighten them. Okay, why have you put a positive sign in there?
Because it's constantly divided. That's just free time.
Full marks. Well done. Really important thing to notice here, that is the biggest loss of marks, that is that your field lines must be equal.
Length or like distance away from each other?
Well, technically just equally spaced. But yeah, I would go for length as well, just for neatness sake. Okay? Dead easy, right? That's a gift. Space 1. The first thing that we should be thinking is this is clearly a momentum question. Yeah? Now there are some important points here that I think we need to be really aware of before we do anything else. They've given us the mass of the spacecraft, they've given us the mass of the zone expelled, and they've given the speed of what's being expelled, and they're asking us, is 8 meters per second a reasonable guess? Yeah, so that's what they've set us up with. Hongbin, I think it's your turn.
So, the momentum of the xenon ion and the spacecraft is equal because momentum comes up.
Okay, right down you go, right down you go. Right down.
I use one and two for.
Yeah. Okay, so I would right above that, so you keep it clear, spacecraft exhaust or ions. Okay, what next?
The mass is
Okay. Yeah, that's good then. Okay.
equals to the mass of spacecraft times
Okay.
You get 8 to not really like that.
Okay, so just show the rearrangement. It's always useful to show the rearrangement. Yeah.
It's like 8.02.
Very nice. You're correct.
Okay, so has an electron, and it's not it's split into two photons.
Okay, so we don't need to worry about doubling our masses because although we've got an electron and a positron, they're forming two photons so each. So one photon will have the energy of one of the electron and positron. Okay?
And so and using HF to find the frequency, which would be
Okay, don't leave out your substitutions. Show your thumbs because otherwise you'll lose marks.
so thanks, Winston. Hope I remember this.
That's it, I think.
And then no, that's divided by that. Ah. Oh. This would be so many things are happening.
Okay, good. You can just draw an arrow to that. Yeah. Okay?
And using the lambda, where that's C. Moving things. So, here, so
Lovely.
that's not a net.
That's done. That's something close to it. Does that seem reasonable? Always important to check. Does that seem reasonable?
Yeah.
Okay, so
I mean,
we're
wavelengths.
okay. So we're looking at something sub-nanometer.
Yeah.
Yeah. So that's good because nanometer. If something's in the hundreds of nanometers, that's in the visible range. We're dealing with something that's below a nanometer, so we're definitely into the gamma range, and that's the right sort of wavelength.
Something around there.
Yeah. So we're fine.
Yay.
Cool.
Hard in the corridor. Induces a magnetic field on the iron core.
We got my laptop.
And
Sorry about that. Carry on.
it induces a magnetic field.
Just go around.
And the alternating current causes a change in magnetic flux. And the flux lines was this. Wait. Cuts through causes the which causes the current to flow.
Very nice. Okay, next.
The rotor tends to cause the magnetic field. Causes
Well, is there a more appropriate equation for this scenario? No, that's not what I'm thinking of. I think we've got wires now, don't we?
Bill.
Yeah. Good.
And so the force causes acceleration.
Okay, I just bear one thing in mind, it says similar to turns. Using turning, what are we thinking about now?
Force changes.
Yeah, because if you think about it, what we've got is, there's our centre rotor, that's our, so this is the sidewell thing. So what we have is the force acting one way, and the force acting in the opposite direction. We've got current going one way, current going the other way. So what do we call that? We've got two forces acting in opposite directions on either side there. Those forms of coupling, force coupling, and that causes a rotation. So what we end up with is it rotating around that way.
Causes acceleration on both sides.
Yeah, the force, so we've got opposite forces acting in opposite directions, so it creates a moment around that bit. And that makes it turn. Okay, last one is nice and simple. Good.
I just going to increase the magnitude, like
Increase the magnitude.
of the current.
Yeah. Well, the applied current.
Yeah.
Yep, that will work as well. That's the third thing. Now, obviously, this one is a state, so we don't need to worry about explaining it. But if we wanted to, why does increase the number of coils help? Not the field strength, because the field, well, okay, yeah, so if we increase the coils that are wrapped around it, yeah, so that increases B, it's supposed to be an arrow, or, remember we've got induced EMF,
Oh, more field lines.
yeah, so what we'd be doing there is increasing N. Yeah, so we get a greater amount of magnetic flux. linkage. Yeah. For this one, for 2, what are we doing? What are we increasing?
G fucking.
Okay, again, so we're dropping t by increasing the frequency. So if t drops, then what we end up with is less, again, a bigger induced EMF. Bigger induced EMF in the coil, in the rotor coil, means that we're going to get a greater amount of force. Then, what we've done is we've increased it by F B I L, and we're increasing I. You shouldn't highlight in red. Okay, happy with that? Cool.
Taken for 1 revolution.
Yep.
And because it's 33 revolutions in 60 seconds.
Yeah.
So 1 revolution would take, which would be 0.82 seconds. So that
Okay.
we would get 2.
Good.
And yes, that's it.
Nice and simple, isn't it? Great. Okay. Ba-ba-ba-ba.
Because acceleration would be the radius times the velocity squared,
Okay.
and then it would just be divided by 100. Whoa.
Yeah, sometimes if you catch it like that, you just think you're writing. Don't worry. Very good. Well done. So we've got strictly specified capacitors. Use the circuit below to check the capacitance of the capacitor labeled 2.2 microfarads, which is a tolerance of plus or minus 30%. Okay. The switch flips between the contacts X and Y so the capacitor charges and discharges F times per second. That's what this bit here is. And that's showing you that she's externally controlling it because she's saying 400 hertz.
Yeah.
So that's what's the answer. So the capacitor must discharge fully through the 100 ohm resistor. Clear my 400 hertz is equal value for F. What are you going to do?
I'm going to find my constant first.
Okay.
Should be C. So
Okay.
so you get 54.
Right.
And then I'm going to find the time because that. I'm going to find the time, which will be 400 minutes.
Yep.
Would be
Okay, so hang on. So your time constant is different to the time we're finding. So you're finding the time period now
yeah,
of the 400 hertz.
yeah. If it was 400 hertz, how long would it
Okay.
take to discharge?
Okay.
And so because I'm gonna just find this, and I'm gonna
Hang
assume
on, are you
that
sure that's what you meant to write? Negative time constant over time constant?
oh, and
Sorry about that.
and I'm going to find this, and if this is a small value, then it should be suitable because
Okay.
we're completely discharged. Forgive me. No, that is. And
does that actually tell? What does that
So
number
this
tell us?
shows that it almost internally discharged.
Okay,
So
yeah,
that-
so it's telling us that what you've actually got there then is Q divided by Q naught.
Yeah.
Yeah, so you're telling us that in the time it takes it to go, in the time it takes to switch X, Y to change,
Yeah.
it's fallen to 1.1 times 10⁻⁵ of its previous value,
So it's big.
which is as close to zero as makes it. Yeah? Fantastic, very good.